Broadcast is now starting. All attendees are in listen-only mode.
Hello, good afternoon all, or good morning or evening, wherever you are. I'll give it just a few more minutes and then we'll get the webinar started on the release update for Genesis 17. So I'll just put myself on mute for another minute or two and then we'll get going. Okay? Okay then, I think we've got most people attending who are going to be. Any others can join as they get along. So in case any of you are not aware, I'm Martin Gambling, the Managing Director of GRM, and this afternoon I'll be giving you an update on the new features in Genesis 17, which is available to download from our site today. Any questions along the way, please do pop them in the chat or questions box of the webinar. Any problems listening to the webinar or seeing anything on screen, do just let me know. Okay then, so I shall get going. So following a very similar format to the last few of these update webinars, I'll start off by giving just a bit of an update, an introduction to GRM for those that aren't so familiar, just a couple of minutes, and that's also going to what's the latest news. Then we'll recap on the capabilities of Genesis. Again, not in any great detail today. We're here to look at the new features before getting into the main bulk of the webinar, which is all about what's new in Genesis 17. And then we'll have a little slot at the end for a summary and questions. Any questions, please pop them along as we go and I can answer them at the end. And failing that, you can of course just email me or support after the webinar. Okay, so the topics we're going to cover today on the Genesis new features will be around these four key sections. So analysis, optimization, the design studio pre and post, and the area of composites, which sits under the umbrella of our OptiAssist tool. Now, in terms of a bit of an intro to GRM, one thing that happened quite recently for us was our biennial conference, OED 2018. For those that weren't able to attend, I would like to just follow up with a bit more information. The presentations are now available on our website. You can see this is a summary of our agenda, and all bar a couple are now available to view. And what we're going to be doing over the next few months is, with the consent of the various presenters, is have a little speaker spotlight. I had one go out a week or so ago for Rob Gow from Robot Bike, and here you'll find a bit more information about the presenter. You can watch the whole presentation again, view the presentation itself in full, and then find out a bit more about related topics. So if you'd like to hear about these different speaker spotlights, then do just register for our newsletter if you're not already on it. I think most of you probably are, but in case you're not, just go to our home page and just register here for our newsletter and we will add you to the list. Okay, so back to the presentation. So who are GRM? As I say, I think almost all of you know us. Today we're talking about the software side of GRM, really our core product, Genesis, as the software that we sell, support and develop around. And then the other side of our business is the consultancy, which focuses on optimization, design engineering, and composites. So what's changed? Just really one of the things to observe in the last year or so has been the growth of two particular areas of our business, which has been component testing, so we can use this now to support a lot of the simulation work we're doing, and also our work in fluid structure coupling, so CFD coupled to structures. That's a particular area of interest that we can help people out with in their engineering challenges. And just taking a look at our software solutions for 2018. So we have our two key products, Genesis and VisualDoc from Van der Plaats. Again, obviously we're focusing on Genesis today. Also, you'll see we've got a new version of VisualDoc released right now, and we'll be following up with information about that in the coming weeks. And then we've got Van der Plaats' other tools, the ANSYS integrated GTAM GSAM, and then Trueform, which also is has a new version for release today, along with our Trueform SolidWorks. So in terms of the new tools out in the market, we've got Genesis out today. Trueform Abacus, this is one for those that are using it. We've got our various customers that are familiar with this tool. Version 4 has been around 4.2 since the end of last year, and today we've got a point release of 4.2.6. This has been really a continual development with our customers who are using it, managing the many different flavors and formats of Abacus input files since we've migrated Trueform outside of Abacus CAE into the wider world of being created in any preprocessor that you like. So that's going well. For those that are in the Abacus CAE world, our integration of 4.2's capabilities into the fully embedded Abacus CAE tool is now well underway, and we're hoping to make that available in around about 4 to 6 weeks' time for those that want it. The GTAM GSAM, this has a release supporting the Genesis 17 install as well, so this is continually developed as an extension to ANSYS, and therefore will have its support of Genesis 17. And then, as briefly mentioned on the previous slide, we've got our new version of VisualDoc, version 9, that's just been released this month, and we'll be following up with more information about that. If you're interested in following up on information about VisualDoc 9 and learning more, then again, just drop an email to support@grm, and we will let you know when the information is available. So, on to Genesis itself. So most of us listening today, I believe, are really learning about the latest features of Genesis, having used it for several years. There are some newcomers to Genesis I see on the webinar, but really most people focus on the optimization side of Genesis. That's what it's best known for, and that's arguably because it's where it's really is a leading tool of all the products out there on the market. But again, there's several customers that have sort of cottoned on to the fact that it's actually a very good Nastran type solver, and its capabilities are growing year on year. And some of those you'll see as new features today in version 17. So in terms of the solving, these are the core solution types in there. So we've got our linear statics, vibration, buckling, heat transfer, and this is now extended, and we've got a good interface for it in Design Studio, you'll see today, and a few more additional solutions in there today as well. And then in the optimization, we've got topology, which is the one that most people cut their teeth on in optimization, but we extend then into really quite a comprehensive suite of optimization capabilities inside Genesis. And the interface for Genesis is, of course, Design Studio, which, again, that's now matured fairly well since its first release, I think around about Genesis version 8. And it's an area where GRM continue to support the development with our plugins to provide specific workflow tools and processes for particular applications of Genesis, such as composites. Okay, so That's the quick intro all done. Now we'll get into the details of Genesis 17. And there's a few key areas of focus on Genesis 17. First of all, we've expanded some of the analysis capabilities, as you'll see, and we'll go through those. We've looked to improve some of the compatibility with other Nastran type solvers, so those being Nastran, OptiStruct, the codes that are sort of established in the marketplace alongside Genesis. There's a new improved workflow for composite optimization, and that one I'm particularly pleased with because some of the work that we do, and it's developed out of some of the application of composite optimization. So we feel quite confident it does actually add a good step in terms of the speed of how you can optimize certain applications of composites. And then some simplified workflows. So if you do want to look at some quick studies, you don't have to get embroiled in so much model build if you don't need to, and can still yield some really good results. So here's some of the highlights that we'll go through. So core solver capabilities, acoustic cavity modeling has been added. It's something I think has been on the wish list for quite a few people for a while, so it's great to see that in the solution. And then heat transfer analysis and optimization. That's actually been brought along step by step since Genesis 15 and 16 with enhanced capabilities for the different solvers. But in Genesis 17, we've got access to it through a great interface in Design Studio, and the capabilities have been fully expanded to all parts of the optimization. Compatibility, that's been a focus really to allow people, when they're just doing analyses, to take models from other decks and run them. And then composites has been some incremental tidy up of some of our OptiSys pre and post. And then we have this new user-defined topology process. Interfaces, we've revised some of the update steps for LS Dyna, and we'll go through that in some detail. And then we've got our process improvements with some of the HexMesh model build and part replacements that I mentioned as the fast workflow processes. Okay, so first we'll step into the analysis side of the updates. And first of all, we'll take a look at the heat transfer analysis. So as mentioned, this has technically been in the code since version 16, but now Design Studio's got an updated interface. It's got a new heat transfer load interface, and it's all fully usable and nice and accessible. Key thing is we've got fixed temperatures, heat flux, and heat power we can apply to the model, and the solution set is conduction and convection solutions available. And these couple directly to the structural solver, so we can have a heat transfer calculation followed by a subsequent thermomechanical directly in the solve. So just to expand on a few details here now, we've actually got a video I'll load here. I won't go through the whole video. This is something that will be made available in the coming week or so to watch in full if this is a particular application you'd like to learn more about. So this video goes into a complete application of the setup process. But I'll just skip through to certain highlights that I think are relevant just to draw your attention to in terms of the new capability. So what we're going to do in this case is we're going to apply a cooling heat flux for a water jacket of an engine block, and then we'll have a heat power source on the cylinder bore. So I'll just whiz through a little bit, and one of the key things I just want to draw your attention to, if I get myself to about the right time, is the fact that when we're putting heat flux into the model, what you'll find is you need to create heat conduction elements, heat boundary condition elements called CH bodies in the structure, and they get stored in a holder inside Design Studio, very much like an RB2 might be held in a holder. It doesn't have a direct property itself, but must be stored. So this video will take you through exactly how to develop that process and apply it and run through the whole heat transfer calculation steps. As I say, if you would like to get hold of that right away, just drop me an email or a chat in this this webinar, and we can make this video available to you. Okay, so once this is present, you can then go and apply heat flux to the model, and you can get yourself to a complete setup here where we can apply these heat flux to the model. I'll just take you through then to the completed setup. So as you can see, this is fairly well detailed in terms of this process. And so the key thing to see here is once it's all set up, you'll have yourself a heat load case and static load case. And inside this static load case, it's taking all the temperature distributions directly from the heat transfer solution. And then, of course, that allows you then to perform optimization based upon the thermal loading combined with the structural loading to optimize for that heat transfer condition. And then finally, just take ourselves to the results data set. Once it's solved, you've got your temperature distributions, which you can see. Having run this model, I think it's perhaps a little bit hot for an engine. We're up into 300s of degrees, so the boundary conditions perhaps aren't the most demonstrative, but it's proving the point very well. And you can see then the expansion of the engine block example. And then we can interrogate the stresses applied to that engine block due to the thermal expansion. Okay. Right then, so moving on to the next key enhancement in terms of the analysis capabilities, which is acoustic analysis. So inside Genesis now, M-fluid property and element definitions can be created. So we can read these directly from any other Nastran type input or generate them directly within Design Studio. And the coupling is fully automated inside the Genesis solver. So it works on approximetry to the boundaries of a structural mesh to form the coupling between the fluid mesh and the structural mesh. And once included, you can investigate your modal frequency response, looking at the pressures in the acoustic cavity. If you want to be able to run this, there are some additional tutorials in the Design Studio examples manual, and I'll show you how you can get to that a little later in some of the new features of Design Studio. One thing just to note is when you are processing the fluid pressures, they plot in Design Studio by default as an X direction displacement. These are pressures, and that's just something just to make you aware of as you're running it. Okay, so in terms of the enhanced support, there's some very specific additions to the input file support to allow users of Nastran and OptiStruct to aim to run their models directly. So if you pass a lot of the input data cards you see on screen now, these will be internally converted into Genesis data format on a pre-processing step, allowing you to run the model directly without the need of editing header and subcase and executive control data and some of the alternative formats for scalar elements and contact and so on. Okay, next up we'll take a little look at the optimization side of things. There's a few nice features I'd like to go through, so just extending on the analysis feature of the thermal structural. This is something we can now optimize for in all aspects of optimization. We have a rapid regular hex mesh workflow, which I'll go through, and we have a new stress targeting approach for topology. So we'll look at that in a bit of detail. I'll describe how that all works and where it can be applied to your optimization problems. And then we've got our user-based composite topometry feature added into OptiAssist, and we'll actually discuss that in the composite section. But I think just to draw your attention to the fact that that's there as a new optimization feature. So looking at the thermal structural optimization side, again we've got two types of optimization we can consider here. Direct heat transfer optimization. And interestingly, there we go. My animation was pausing for a brief moment. So hopefully you see that animating on screen now, like some strange plant roots. But so we've got examples in the Design Studio manual. And the one you're looking at here is 3.37, which is maximizing the heat conduction in a plate. And so this is a pure heat transfer topology optimization. But you can also perform combined thermal mechanical optimization. And one of the key strengths of this is that the topology optimization will consider both the distortions due to thermal loading and how the topology itself will change the heat transfer during the calculation. So this is example 336, and it takes you through how to perform a combined thermal mechanical, where we're looking to maximize the stiffness of a structure whilst minimizing the peak temperatures that result in it. It's actually quite an interesting area for us, something that we're looking into more, and so we'll be expanding our experience of this particular subset of optimization. So if it is relevant to you, we aim to be able to provide some good detailed support as you look to apply it yourselves. So next up, we've got a new process flow. There are quite a few. We do it ourselves internally, and we've recommended it to support in the past, which is sometimes to get a clean result for optimization, maybe to speed up large problems or just to get a nice clean solution. We've suggested using our RDM tool to replace the TET mesh of a design space with a nice regular hex mesh. And so we do that so much really as a company, and we find the results faster and cleaner, that we developed a new part replace function as part of the GRM design toolkit. And this has been expanded also to support direct creation from your Cad data through STL, and we'll go through that in a little detail now. Now, one of the key observations is taking the simple example here of a rocker meshed in TETs and then in regular hexes, is as well as what we feel are cleaner results, you can actually see a performance improvement in the solution, and that comes down to simplifying the optimization problem itself. So in this same design space volume, we have around about 120,000 TET elements versus about 20,000 hexa elements. Now, the solution time, there's very little difference in it. The TET element is not really the solve issue, it's the number of grids or nodes that dictates that. But when it comes to the topology optimization and the process of the optimization step, we've greatly simplified the number of design variables from the 120,000, i.e. one per element, down to 20,000 here. So taking just this example here, the solution time went down from just shy of 600 seconds to under 200 seconds. So there's a speed up as well as for cleanness of the results. So the benefits of this are obviously we can get a nice clean solution, but it also allows us to investigate mesh refinement for our topology quite quickly, because we can do the hex mesh in literally a matter of seconds to create the mesh. So we can run it at different mesh refinements. So we can start our initial scoping studies at a coarse level and then switch to a more refined level when we're getting down to the level that we want to finalize. And then, of course, we can look at meshing directly from the Cad data. And this has really come about. So in some instances, you really just want to be able to create a mesh of a design space very quickly and apply your loads. So it seemed a logical step to be able to just create this hex mesh, apply your loads, and run a topology directly from it. Now, the video I've got on screen is going to take you through the two sides to this new function. First of all, I'll take you through the part replace. So here's the interface. If I just whiz back a little bit, you'll find here we've got our wrap hex mesh function inside the design toolkit. And what we're able to do is choose which part we want to replace, whether we want a uniform or custom mesh. So custom allows us different sizes and the different axes of our mesh, and that can be quite suitable for certain types of optimization. And then we've got extended advanced functions, so we can keep the previous mesh, we can choose what parts we're connecting to, and so on. In this case, we're just going to connect it automatically what's adjacent, give it a 3mm mesh, and hit go. So what this does is it just simply replaces the existing tet mesh, and it connects in the same way that we recommend through our RDM tool, which is a selection of make connectors between the parts. Okay, and that's how that works. So the next example is just to show you how the process can work to speed up the process from Cad into sort of rapid assessments of components via the STL interface. So here you'll note we can change to the STL file rather than what's inside your Design Studio database. And here we have the most exciting rocket ship you're ever going to see. This is courtesy of Microsoft's 3D rendering tools. So just to see there. So what we want to do is create ourselves a hex mesh of that space. So we just simply pick our STL, define our target mesh size, and away we go. You see it goes away, processes this, and it's actually really quite a quick tool to generate your mesh. So you can go and perform your topology on that, subdivide it as you need to into designable, non-designable, if applicable, and run your optimization. Great. So next up, as a feature, we've got the new von Mises index stress-based topology approach. So this is a new constraint effectively inside Topology Optimization for Genesis, and it allows users to minimize mass fraction as an objective whilst keeping a watching eye on stress. Now, should draw attention, it's not a direct stress constraint, so you may get some elements above and below, but what it is a very, very rapid optimization process. It's easily comparable with a classical fixed mass fraction and minimized energy approach. But it's basically monitoring the VM index to achieve a minimum mass fraction. The way we see it, having tested it a little bit, is it's an alternative to the stress constraint procedure that we've developed at GRM. I think both have their relevant applications, and I think those that are quite experienced with Genesis will probably see some good benefit from combining the two processes as we go. So this is the existing process if anyone wants to use that one. So I'll just take you through the setup because it's worth noting how it's been defined as a setup within Design Studio and then the respective data inside Genesis. So first of all, we've got our simple hook example. You can see our stresses are currently around about 50 megapascals. So we're going to perform a topology that says minimize mass fraction and make sure we don't exceed 60 megapascals. Seems a logical starting point. So the way that it works in the VM index, if I just pause here for a moment, is for all the components we wish to consider stress as a limit for, we'll define this SS field. So this is, if you dig into Nastra and Genesis input, this is either shear stress or a von Mises stress limit. So we'll add our stress limit into the materials that are referenced by all the parts where we want to be limiting the stress. So in this case, I'll be putting in 60 megapascals as my target for the part. And having done that, we can go through our usual setup process. So in this case, we're going to just do a simple topology, minimize mass fraction, as you'll see. One thing to note, having tested it myself, it's not something that you have to do, but my personal recommendation is I tend to start from an initial mass fraction of 1, and that's the rationale that you're starting from your solid lump of material and reducing the mass fraction down to a feasible limit in your solution. So you see that's there. Other than that, the setup of the fabrication constraints, if present, are all exactly the same as any other topology. So next up, we will define our mass fraction as the objective. So we'll just put minimize mass fraction. So traditionally in the past, we'd suggest users would run 3 or 4 fixed mass fractions and minimize strain energy. So here we don't need to do that. We can now minimize the mass fraction. And you'll note that what we have is this von Mises index that's present as a new response that we're able to constrain. So the way it works is having defined our material limit on a material, and if you do have several materials with different material limits, you can define the different limits on the different materials during your model build, and then you simply define here an upper bound of 1 for your von Mises index, and that will then apply the respective stress limits to all the different materials in your model. Okay, so once that's done, we can just hit solve and go and run it. So I don't think at this point we want to stare at the solution, it just takes a minute, but I shall just whiz us through, and you can see the way it's bringing the mass fraction down to our target solution. And so we'll bring in our results. We'll take a look at the analysis and optimization results for that last cycle, just so you can see the sort of results you get. So it's a hook, pretty straightforward, and we get our result. So we got our 33% mass fraction for our design. And if we take a look at the stresses in a moment, so this is the topology result, and here's the stresses, you'll see that we are 58.4 as our stress limit, so just falling within the limit. Now I think what I probably draw attention to is that it's still fundamentally a sort of work energy based function as I understand it. I'm still learning myself, so it's not going to develop a cutout in here to relieve stress, allowing a different solution. It's still looking at a stiffness and stress based solution, but nonetheless a good step forward, I think, in terms of solving very quickly for stress in your topology optimization. So on to our next step, which is Design Studio. And so what we've done is we bundle in some of the features in the toolkit together, so it's a bit clearer. So we've got our general usability updates, and there's quite a few subtle but good time savers. Good, I've got some questions. I shall answer those at the end. Just spotted those popping up there, folks. Thank you. So looking at the usability updates, we've got a nice little step. It's a step forward in terms of learning, self-learning through the Interface Design Studio. We've got manual access, we've got view, import, export, renumbering, some quick node move and replace, enhance feature picking, and this is a very useful one, finding badly formulated RBE3s. It's something we've come across with large models quite a lot, that people are running models with free floating nodes in RBE3s, which is not a good thing. So we've got a tool to help identify those. And then we've got some additional features in the post-processing as well. So what I'll do, I'll run through a little video just to let you see some of these features. So first of all, a nice step is the manuals for the Design Studio examples. These are all the over 1,000 pages of new features. You can work you through examples. I've mentioned some in this webinar, and they're all accessible now via here. And then we've got our analysis and design reference manuals. So whilst it's not full contextual help as yet, what I tend to just recommend is if you load the manual and expand out the bulk data section, is a very good point. You've got all the bulk data cards in your manual, and then if you're working on something, so here I'll just take an example of defining a contact. You can see I wanted to create, for example, a BC pair. So most of the entities you create in Design Studio have got the actual keyword defined in brackets, so you know what you're looking for. So when you have something such as BC pair, we can go, okay, I've got that loaded. where is that in the manual? So I can just hop across to my manual that I've loaded up, and you'll find, hey presto, there is your BC pair and all the information relating to it. So it's a step forward, I think, in terms of the documentation and accessibility, which I'm really pleased to see. So next up, we've got some views. So you've had a view catalog in Design Studio for a while. A particular little feature I find is if I have one model and then I want to match the view in another database, another model, that's a bit tricky. So what you're able to do now is simply export and import your views. So you can see I'm just on screen importing my views. Here it is, and it's done. So that's just a nice little extra feature, I think, in the tool and how it all works. Next up is one that I have to smile at. It's one that's been around for quite a while inside Design Studio. For those that know about it, there'll be those of you listening that will know well it's there, and those that will be wondering, how do I renumber things inside Design Studio? So previously it was a function whereby you could hold the shift key down and modify, and it would access the secret renumber panel. So now we've got a really good direct renumber panel, and this works for, I think, almost all of the functions and entities inside Design Studio, so you can renumber your model and organize it accordingly. So that's nice to see. Okay, so next is this new function where we've got a find problem elements feature in the element panel, and at this stage it has just the one new function, and what I anticipate is as the releases develop now, we'll see more and more of these checking options available. So we might have distortions, duplicates, and so on adding in future releases. But here you'll see once we do a find bad RBE3s, it's selected an element, and of course I have an example in this model to show it, and you can see that in this model I've got a free floating independent node for an RBE3. It's something that can happen quite commonly in models, but it's really not good from a numerical point of view, because I think it's my understanding that that node can be automatically SPC'd, which then will start to create some strange behavior in your model. So just to couple up with that, there's a new grid function that you'll see. So we've got our quick move grid to grid function, and with this, if I just click on that quickly, you'll see I'll be able to either move or merge two nodes together. In this case, we'll just merge it in place. So we'll grab the node and replace that there, so we can fix our bad RBE3. So just some more little steps to help the usability day to day when you're inside Design Studio. And these little features do make life an awful lot easier. They often seem trivial, but they make a lot of difference when you're sitting working in a tool all the time. Okay. So next up, as a general enhancement, you'll see, and this has very much come from a user request, is we're able to now just plot the deform scale. Often people see things moving and get a bit panicked if it's moving too much or whatever. So you can see here this hook is actually moving at 314, I should say, times its actual displacement. So always worth bearing that in mind. So that's something that you can display. And I guess for those that aren't so familiar about the options, so that's added in here in our Defamation Options. You can see it's something you can turn on and off. And equally, you can turn off all the other features if you weren't aware in this area, and you can control how the animation might look inside, include your undeformed shape and so on. So you can start to move that around. Okay. So next we're going to move on to some of the new features. This particular one is added in to the plugins. So many times we have multiple load cases. We found that we want to generate a quick summary of where the overall system is working, rather than sitting one by one going through our load cases. We can get a nice envelope result to get the worst case. So if we just take a little look at this. So here we've got one of our tutorials in the Composites manual, and we've got 4 different load cases. So you can see we've got rear load, lateral load, and 2 towing loads, and each of them have got their respective areas of failure index and stresses induced in the part. So what we'd like to do is just very quickly get ourselves an envelope result of those. So it's something that you can achieve, and we've been providing as a support function to people that have asked over the last couple of years using the synthetic results panel in Design Studio. So what we've now done is just enhance that, so you can just simply directly pick the responses, and it will go away and create that synthetic result for you as an envelope of the multiple results. So you can see that that is capturing the failure index across all the load cases, so you get a broader picture of any issues in the structure. Okay, and then just a last function to look at, if I just take a little look, is in the Manage Results data sets, you've got this synthetic results section, and there's been some additional new features added into this where we can smooth the results in a number of different methods. But again, just to clarify, if those aren't familiar, you've got quite a selection of functions here, and you can build up compound formulae of responses, which can be really quite powerful in your post-processing or an understanding of a system. So I'll just whiz through here, and actually what we're going to do is just do a bit of a smoothing result by way of a convolution. I will just move quickly through. I think the key thing just to show you is as a new function, you can start to smooth topology results. It's very much just a user preference whether they want the direct results or not, but you can see here we can generate a smoother, cleaner result of topology. Something if you're maybe going to 3D print a part, that could be quite relevant. Okay, next a good feature. So whilst we're busy generating our part replace function in Design Studio's plugins tools, we've got some nice features in the core of the element creation in Design Studio. And this here is how you get to it. So we now have a generate elements from voxel covering. So it's a similar logic for hex mesh creation. It doesn't do replace parts in the same way. It doesn't work with STLs. However, what it does do is a great extension for additive manufacturing type problems. So we can either create a solid mesh or a lattice mesh and so on. And there's different rules and how you can do that and orientations that you can create it on. So if you just take an example here, this is quite a nice one, I think, if you are looking at lattice-based additively manufactured parts. So here I've taken an example of a brake caliper design space. You can very quickly create a skin boundary and a lattice. You can choose how that lattice is generated. And then the great thing about that is you can add topology, size and shape to the lattice, so you can work out where you do want any beams or not. You can size the beam diameters and even do some free shape on the node points to optimize their orientations. So this is really quite an extensive tool to allow you to optimize for additively manufactured lattice type parts. Next up then is another step in terms of the usability of a topology process. Is if you've done your topology very quickly, you get your analysis and optimization results direct from the topology solution. But if you want to throw away the low density elements and just assess the part itself, we now just have a new threshold deletion tool. So you'll find that in the toolkit. You just pick your topology result, the part you wish to consider, you choose your threshold cutoff for your element densities, and it will remove the design data, delete the low density elements, and prepare the model ready to do an individual analysis of that setup. And then I think this is the last update in the Design Studio interface, and it's relating to LS-DYNA based optimization studies. So I think it's relatively common to linearize a nonlinear case. People do it quite a bit, be it in the example I'll go through here with an automotive body, or even just a small component where you may just perform an approximate optimization linearly, and then you want to do that validation in the nonlinear model afterwards. So previously we had a button in the toolkit which would allow you to export a Dyna keyword, and what we've concluded looking at that is that really to support creating a keyword fully is almost too complex. There's a lot of editing to do afterwards. So we've changed our approach, and now we've got the ability to just update an existing Dyna deck for shell thicknesses and for nodal positions. See, I keep pausing every time I stutter. It's because somebody asked me another question. So I keep trying to read and speak at the same time, and whoever just sent that, they know who they are, will know that I can't do two things at once. Okay, so yeah, we've got the ability to update the thickness based upon a sizing or topology optimization, and update the nodal coordinates of your Dyna deck based upon a shape optimization of some kind. So what I'll do, I'll just take you through a little bit of a demonstration of that. So here we've got our classic Ford Fiesta impact. So it crashed into the wall, away it goes, and I've just contained it to a very small optimization here, just to show the just to show the example. And one of the key things really why we've put this method in is because so often with these large scale models is you have include files, and trying to write out one big bulk from an optimization is always a challenge. So here we've got our body and white include, and this is actually where the optimization is done. So we've thrown away all the other parts of the model, and we're doing just a optimization of the body in white, and in fact just of the parts you see on screen now. So moving across to Genesis, we've got our model already defined, and we've put masses in, and we've developed our load cases. So this is our linearized crashed load case, and you may well create that either through our tools in the interface, or you're doing that manually yourself. Either way is completely valid for this model update process. And so what we see is in this bulkhead, we've done an optimization whereby we have just simply said, okay, we can add an extra 5 kilos, make it stiffer. It's very simple and sort of a slightly non-physical case. But you can see on screen now, or you should be able to see on screen, our updated thickness distribution. So what we want to be able to do is just simply update our Dyna deck, not worry about creating a new one, splitting it out into different includes, just update directly the include file that is relevant to this particular result. So what we do is we just go into our plugins tool, update the shell thickness, and we'll do that now. And so it walks you through the process. So we pick the result set we want. If any of you are wondering why it's gone green, it's just because the particular process defaults to the total thickness range of all the model, not just what's on screen. So no shocks there. But whilst talking, I'll just go back a little bit to here, and you can see there's two different modes of export type, and this is actually driven by sometimes the need for further manual iterations post optimization. I think it's all about adding optimization into the engineering process, not replacing existing processes. So what we've got is we can either export as discrete shell sections with a thickness increment, or we can do it directly to the element shell thickness card. So obviously this, if you're in the world of Dyna, you'll understand exactly what that means. And in this case, we're going to do the shell thickness. So what we do is we pick first of all the include file we want to read as our master file. You can either just let it add an updated string to the file name, or in this case, I'll specify the output file I want. So that will go and run and create you your updated keyword file. Great. And just to show you, so here we have on screen just a thickness contour of the particular include file updated using the shell thickness option. And you can see how that's done exactly as we would expect. That matches what's inside our Genesis result, so we can run that in Dyna. One of the key things I find is the other option we'll show in a moment, where we split it into parts, is quite useful if you want to then do further subsequent iterating. You get some more discrete thickness results, and you can edit them more readily afterwards. So you can see here the parts being broken into different properties. I've kept this quite simple just for this example with a very large increment of 1 millimeter. So it's just shifted into sort of 2 and 3 millimeter chunks. You can refine that via the UI to what increment you want to consider. Okay, so that concludes that one. So, last but by no means least, it's very much a key part of what we do with Genesis is the section on composites, and I'll just go through that now. Now, there's two changes really, one significant, one quite minor, but I think they both make quite a nice step and improvement to what's available in Optisys and the composite interface. We do actually have quite a nice roadmap as well as some of the new features already in version 18 we plan, so if anybody's interested in learning about that, they can contact me directly and we can discuss that. But if we just start looking at some of the updates, this is a feature that was added to, I think, some of our customers as sort of a point release through 16, and this is now formally in the Genesis 17 release, which is the allowing of editing multiple plies. It's one of those small but significant effect tools. If you do have a few hundred plies in your laminate and you want to change the material type for 100 of them, it's very boring to do it one by one. So you can now just do that manually with the multiples in one step. So just a bit of tidying. You can edit material, thickness and angle across multiple plies. So then a bit more detail in the next topic, which is something we're calling user-based topometry. If you get into nitty-gritty, it's actually kind of a mix between sizing and topometry. But I think if you see how it fits in the interface, it'll become quite clear, which is what I'll aim to do in the next few slides and video of how it works. So just to clarify that those that maybe aren't so clear, I think most of you will be, but what is topometry? Topometry is in the context of composites, is the automatic subdivision of your ply into smaller patches through an optimization, such that you can then develop ply shapes. And there's two modes within Genesis. We've got grid-based and maximum elements. And I think most of you are using grid-based, so you'll define your length in X, Y, Z, and it will chop up your plies and optimize the thickness accordingly. The benefit of this process is it really does give good freedom in terms of developing the ply shapes. However, the limitation is the shapes can take a lot of time to process. We've got, I think, some pretty advanced tools in terms of the updating of your laminate based upon the results. But even so, there's still a good chunk of work in developing your ply shapes from this. And sometimes in the pressures of developing a laminate, time can get the better of you. So what we've really aimed to do with a user-based topometry is give the user control of the patches that are being generated. And actually this process has really developed through some applications of composite optimization that myself and some of the guys in the office here were doing, where simply time wouldn't permit the investigation of topometry and all this freedom for the plies. But equally, we didn't want to confine ourselves to just dictating the ply shapes right from the outset. So this is why it was quite a nice implementation to add. So what we've got is inside Optisys is a new option in the topometry set creation, as you'll see, that allows users to define their own patches in the optimization. So you can see on this example here, we've got some predefined patches for certain attachments, and then we've just zoned it in a way that we'd be happy when it gathers up those patches to make plies almost directly to manufacture, and that's really its aim. So the user is going to invest some time in these ply patches with the aim of really saving a huge amount in the optimization step and the post-processing and then subsequent release of a design. So I'll take you through this. This is a tutorial that's in Genesis 17, so you can work through this yourself to get a feel for how it all works. And what we do, so I've taken this example which has got a classical topometry already set up for 2 plies. So we've got some UDs in 0 and 90, and this has got the standard 50 by 50 by 50 patch that we're putting in for our division of the ply shapes. So if I just hop across to the second model in this database, that's what Genesis is working with. So it's going to chop up the model into these patches in terms of the ply thicknesses, and then it'll gather those together into ply shapes once the optimization is complete. So we can take a look at that, and so this is the kind of result we're getting. So it's actually some small patches of UD reinforcement in this example. And when you start to then look at how those thicknesses that you've seen are achieved through physical plies, which we do here, so we're just going to update our laminate, you'll see that we do get some rather interesting patches. So we can start to understand what the optimizer is doing, but we're not going to be putting plies of those shapes on our structure. So what we normally do is go away and start to edit our plies, tidy it up, generate a new laminate based upon these, and then we might perform a subsequent sizing optimization of those plies, because that leap from the topometry to the optimized solution to the manufacturable solution, I should say, is quite a big one. So, and there we go. We've got our patches tidied up. So now what we're going to do is we're going to hop to applying the process with the new user topometry. So what we're going to do is, if you notice, you edit the topometry set, and if you expand the coarsening method, you'll find there's a new user patterns menu available. And when you access this, we can go and create and edit our patches. So there are several different methods available here, but what I'm going to do is I'm going to just take you through the user patches, which is personally for me the one I certainly would use the most as a process. So what you're able to do is you can choose which laminate you want to define your patches on, if you've got more than one laminate in your composite modeler setup. You can choose a mirror symmetry plane. So what it does when you choose the mirror planes, it will, as a pre-step for the subsequent patch generation, it's going to just work out which elements are paired. So it facilitates the next step, as you're seeing now. So we're going to create this patch on the side. We'll add that, and what you'll notice is immediately it's created two patches. So these are automatically matching, so you can see either side of the structure, and that's where the symmetry tool picks up. And then we're going to do another patch here at the rear end. So you can see just cleaner patches that we want to consider. We've added that, and again we've got our two patches automatically managed with a symmetry approach. So we've defined those for our one set, and actually what we're going to do then for our 90 ply is we're going to just have no symmetry in this case, because the plies will just run across the width. So again, we'll create a new user pattern based approach. We won't use symmetry, and we're just going to band the structure into possible ply placements. So we just add one there. There's a function down here which I particularly like, which is you're able to hide elements that have been used in a pattern. So when you do have something large as an application to do your user patterns, if you have that checked, as you keep adding your patches into this list, the model on screen will quietly, piece by piece, disappear away from you until you're left in theory with nothing on screen, which means you fully defined all your user patches. So you can see here, we're just going to band these. You can pick either by drag window, and this is where you can use the feature angle. You can select visible in the viewport, all the best picking options to find your best way of defining these patches. So we add all those, and you can see that they're defined. So we accept our set. So these patches are stored in this set menu, and we can assign them to the topometry setup here. So we'll go away. The rest of the optimization has already been set up, so we don't bother with any of that. And we'll just go and run the optimization very quickly. It's a very, very quick optimization to get through. So I'm going to do that. So whilst this is running, I'll just apologize. We are just running a little over on time. I hope to wrap this up by 4. So this is the last example, so we're pretty much there. If anyone needs to dash, they can ask questions with me later. Okay, so we brought these results in. And with these in, we can see our new results. We'll just plot our layer thickness. And hopping to 3, you can see now we've got much cleaner divisions of our thickness distribution from our topometry on where the plies need to be. And so when we go to our next step of updating the laminate, so update composite model laminates function, we pick our laminates we want to update, the results data set we want to use. Now when we go into our composite modeler, you'll find that the ply shapes really are nice and straightforward, and see it's for the user to decide what they want here, and they get that control over their solution that they want. So for us, we see it's quite a nice, sort of almost arguably a step change in the types of optimization you can achieve with composites. And I think in terms of how it fits into the workflow, that depends on what time you have available. So I think we still, in many ways, recommend performing the standard topometry whenever possible. It gives you that freedom of design. You know, if we look at our process, we do that, interpret your ply shapes, do your detailed sizing, and update your design. I think key thing though is when there are time presses, you can take your ply shapes, effectively put your candidate plies that are almost the plies you're going to make, but you can subdivide them how you want to. Optimize that, update, and you're pretty much straight to a design. So that's almost the fastest route. Some compromise on pure performance, but much faster. And then an alternative approach, which subconsciously I realize we've already been using when we do it this way, is to perform very quickly a standard topometry, and just to get an idea of where plies may want to be. So we'll do that as a quick study, and we'll use that to guide some of the subdivision. So we're keeping in mind our topometry results and our manufacturing in the ply shape division that we put in, and then we get our optimization result. So I think it's quite a nice, exciting step in what we do with composites. Okay, so with that concludes the updates. One of the questions I've seen, which is quite nice, is when will Genesis 17 be available? Thank you for that question. And the good news is it's there. Of course, completely calmly and relaxed, we were getting that ready, as we all know that how it happens in business. The tools are installed, uploaded, and ready to download now from our website. So you'll find the Genesis PC install, which is Genesis and our plugins. For those of you that are sourcing Genesis or elsewhere around the world, we've got the plugins that you can add in if that's applicable. Obviously, if you've got the standard Genesis install elsewhere, and then the Genesis solver installation is there as well. So we've got that available. Spot my typing error, consulting. Other news, so if you're interested in working out how to get to grips with Genesis 17, there'll be update training starting from August, and you can book that now. So just drop a note to support and you'll find out about that. Or there can be application-specific training. So if there's a particular area of interest, we can support training on, say, the heat transfer, for example, the composites, new features, or something of your own application. Do let us know, and we can support that training. Any other questions? Just contact support@grm. Okay, so that wraps up the presentation. I'll just have a look. There have been some questions that have appeared along the way. If there's any more from any more of you now, please do pop them onto the questions board. What have we got? So what is the von Mises index? Is it a shear stress related one? Okay. Not really. It's working on the von Mises stress, so it's looking at essentially a resultant element stress averaged across the elements internally. So it's working on an internal von Mises stress index. The very honest answer is I'm still learning a bit more myself about exactly how it works. But I think essentially it's somewhere between stress and strain energy based, but it is allowing us to do that minimized mass fraction functionality. Next question, do you recommend to use a stiffness constraint as well as stress? Not necessarily. In the case of this new VM index, it's really quite capable of just setting a stress target and hitting go, and that will minimize your mass fraction. It works quite well, and I think because of its almost consideration of the strain energy, it is fundamentally working on a stiff structure at the same time as monitoring your stresses. When's it available? Now. Is the envelope results an addition to the different results or an optimized solution? So yeah, it's just simply a post-processing operation that allows us to, if we have multiple load cases, we want to get a snapshot of the work being done by a structure or any overall issues. It's the envelope plot is a way of gathering it all together in one single plot. It's quite useful to present out how a structure is performing. Okay, so I have a question here about the deleting of elements. So I think this is relating to the part replace function. So it doesn't delete any elements other than the part it's replacing, but it follows a similar logic to how the RDM and make connectors works for those that are familiar, which is the part being deleted will always be the dependent nodes of the connected elements. So it should always prevent the dependent node issue occurring. And for that lady who asked the question, thank you for saying sorry. Okay. For updating dyno thicknesses after a topology optimization, does a feature exist that simplify a dyno thickness distribution with only a few parts? Well, yeah, you can apply it, so you can choose exactly which parts you're going to apply the thickness update to. So if you have optimized an entire model, you can just simply put on screen the parts that you wish to update, so the few parts you want to update, and it will only update those in the keyword file. Okay, we've got some good questions coming through here. Just a quick little pointer from one of our good conscientious chaps on support. If you have feature requests from today or afterwards, please do email them to support@grm-consulting.co.uk. I'll put it back on screen, this one. So it's not just for any questions, feature requests, please let us know. I really want to make sure we get those in. Yes, the presentation will be available afterwards. All being well, it's being recorded, and it'll be available via the go-to webinar page to watch again if you want to. And those of you that haven't attended, you'll be listening to this afterwards, hopefully. And do you have a quick setup guide of the new stress topology? Not so much, but there is a tutorial within Design Studio. So I'm just going to hop out here of the presentation, and I will fire up Design Studio 17, and I will see if my newfound excitement at manuals works. So if we go to our manuals, Design Studio examples, if we go to our Topology Optimization examples, there should be one with our new VM index. Just got to try and find it. Heat transfer, thermomechanical, stress constraint. So here we go, topology example 3.38, and that will take you through. That's the exact one I've just actually run on screen. So this takes you through the setup and the result that you'll get. So that's available for you, and you're very welcome. Excellent. Okay, so if there's no more questions, I think I shall close the webinar. And but I say, do please get in touch if you do have any more questions. And yeah, thank you very much for attending, and enjoy the rest of your days. Okay, all the best. Bye-bye.